Good afternoon, students. Welcome to 34th lecture of refrigeration and air conditioning subject. Today we are discussing the unit 4. So in the last class we have completed unit 3 successfully. We have completed all the topics related to the unit 3. Now we are in unit 4. Calculating. We are in the unit 4, taking the first lesson from the unit 4. So in the unit 4 we are having the concept of vapor absorption system. In that vapor absorption system we are having 3 to 4 types of refrigeration system. Later we are having the other topics such as see here. So in this vapor absorption system we are having the calculation of maximum coefficient of performance, the description and working of NH3 water system and lithium bromide water refrigeration system, that is 2-shell and 4-shell system. Next, the introduction to the fluid absorption system, 3 fluid absorption system or Electrolux refrigeration system, their salient features. That is the topic we are having in the unit 4. Coming to the second topic, we are having steam jet refrigeration system. So in the steam jet refrigeration system, the working principle and basic components. The working principle and basic components. Next, the principle and operation of thermoelectric refrigerator, vortex tube refrigerator or Hill's tube refrigerator. So these are the small topics we are having in this steam jet refrigeration. So in the unit 4 we are dealing about vapor absorption system, but in the unit 3 we have already dealt about the compression absorption system, right? So here we are having vapor absorption. There we have already completed other type of refrigeration system, and we are having the steam jet refrigeration system. Coming to the unit 5, so we are having the introduction to the introduction to the refrigeration and air conditioning. So we are having introduction to the air conditioning, that is psychometric properties and processes, characterization of sensible and latent heat loads. The next one is need for ventilation. Need for ventilation, consideration of infiltration. Next one is load concepts of RSHF, GSHF problems, concepts of ESHF and ADP temperature. Next, the requirements of human comfort and concept of effective temperature. So the second topic in the unit 5 is the requirements of human comfort and the concept of effective temperature, that is comfort air conditioning system. Next, requirements of industrial air conditioning. Requirements of industrial air conditioning and air conditioning load calculations. So these are the topics that are situated in the unit 5. Next, coming to the unit 6, air conditioning systems, classification and equipments. Next, cooling, heating, humidification and dehumidification. Next, filters, grills and resistors, fans and blowers. Heat pump, heat sources, different heat pump circuits. So these are the topics you are having in the unit 5 and 6. So we shall complete these topics within our expected duration. So now we are dealing the vapor absorption system, the introduction to the vapor absorption system. So this is also one type of refrigeration system among the compressor type of refrigeration system. You are having a vapor absorption refrigeration system. So this is the oldest methods of producing the refrigerating effect. Okay, so among the three, this is the oldest method where we are used in a long time for refrigerating effect. The principle of vapor refrigeration system was first discovered by Michael Faraday in 1824 only, right? In 1824, while performing a set of experiments to liquefy certain gases. So whenever he was doing some experiment in the laboratory, so while doing the liquefaction of gases, he found how to get the refrigeration effect by the vapor absorption system. So he was he was the first man to discover at 1824, while performing a set of liquefy certain gases. The first vapor absorption system machine was developed by French scientist Ferdinand Carré, right? The first machine was developed by a French scientist Ferdinand Carré in 1860. This system may be used in both the domestic and large industrial refrigeration plants. Okay, this system may be used in both the domestic and large industrial refrigeration plants. The refrigerant commonly used in a vapor absorption system is ammonia. Okay, so in the vapor absorption system, what is the refrigerant generally we are using is ammonia's refrigerant. Okay, so that is a very simple topic of vapor refrigeration system. So the first point is in 1824, the scientist Michael Faraday was first invented the vapor absorption system by liquefying some of the gases in some experiments. Second point, the first machine was developed by French scientist Ferdinand Carré in 1860. Later, this machine was used for both industrial applications as well as domestic applications. Next, this was the oldest method of getting the refrigeration effect, and the vapor refrigeration system uses what type of refrigerant? It uses ammonia. Okay, it uses ammonia. Next, the vapor absorption system uses heat energy. The vapor absorption system uses heat energy instead of mechanical energy. Okay, so in case of using the mechanical components, mechanical energy, it uses which one? Heat energy, as in a vapor compression system, in order to change the conditions of refrigerant required for operation of the refrigeration cycle. Okay, so it raises its temperature and pressure higher than the cooling agent in the condenser, so that the higher pressure vapors can reject heat in the condenser. So the liquid refrigerant leaving the condenser is now ready to expand to the evaporator conditions again. Next, in the vapor absorption system, the compressor is replaced by an absorber. So in the vapor absorption, in the vapor compression law, other type, but here in the vapor absorption type, the compressor is replaced by the absorber. That's why vapor absorption system. So you are having an absorber, a pump, a generator, and a pressure reducing valve. These components in vapor absorption system perform the same function as that of the compressor in vapor absorption system. So here the vapor refrigerant from the evaporator is drawn into the absorber, where it is absorbed by the weak solution of a refrigerant, forming a strong solution. This strong solution is pumped to the generator, where it is heated by some external source. During the heat process, the vapor refrigerant is driven off by the solution and enters into the condenser, where it is liquefied. So the liquid refrigerant then flows into the evaporator, and thus the cycle is completed. So this happens in this vapor absorption system. So what does it happen? So during the heating process, the vapor refrigerant is driven off by the solution and enters into the condenser when it is liquefied. So during the liquefied, the vapor refrigerant is processed. Therefore, the liquid refrigerant flows into the evaporator. Thereby, the cycle gets completed. So this what happens in the vapor absorption system compared to the vapor compression refrigeration system. Next, simple vapor absorption system. See here. So the diagram shows the simple vapor absorption system. So see this diagram here. Now see the diagram here. So the low pressure ammonia vapor is passing the low pressure from here. So we'll say starting here. The low pressure ammonia vapor is passing into the absorber. Thereby, in the absorber, you are having a cooling water. So the water is going in this side and circulating and again coming outside. So what happens here? The absorber will absorb the heat of ammonia vapor. Then it pumps the ammonia vapor to the strong solution having QP to this generator, adding Q generated in this generator process where you are having steam or heating coil. So the generator is run by the steam or heating coil. So from the generator the heat is supplied and again it is flowing to the weak solution and pressure reducing valve, and the balance thing is going to this high pressure ammonia vapor. So during this process heat supplied, so some sort of solution is going again back to this cycle. The other balance is going to the high pressure ammonia vapor system. Later, from this system it is going to the condenser, where the condenser is getting in the condenser the vapor is getting cooled. Okay, the vapor is getting cooled. The cooling water is one side, the cooling water is going outside, is getting cooled. Thereby the heat is rejected at this point QC. Therefore, the ammonia vapor from condenser it is passing into the evaporator by receiver and expansion valve. Here in the receiver, in the evaporator, the heat is absorbed. The heat is absorbed. So in the compressor, the heat is absorbed, and from the evaporator again it is passing to the absorber. So like this, the cycle gets repeated. Thereby the vapor absorption refrigeration system moves in this direction. Okay, next. So in the simple vapor absorption system, it consists of what? An absorber, a generator, okay, a pump, a generator, and a pressure reducing valve to replace a compressor of vapor compression system. Okay, the other components of a system are condenser, receiver, expansion valve, and evaporator, as in case of vapor compression system. So you have just a minute change for this vapor compression and as vapor absorption system. Okay, next. So here in this system, so whatever the figure you are shown in the previous slide, here the low pressure ammonia vapor leaving the evaporator enters which one? Enters the absorber, where it is absorbed by the cold water in the absorber. Then the water has ability to absorb very large quantities of ammonia. Okay, the water has the ability to absorb a very large quantity of ammonia vapor and the solution. So thus formed is known as aqua. So here it is pumping here. So it is forming is a aqua ammonia. Now This aqua ammonia absorption of ammonia vapor in water lowers the pressure, and the absorber which runs in turn draws more ammonia vapor from the evaporator and thus raises the temperature of solution. Okay, na? Some form of cooling arrangement, usually water cooling, is employed in the absorber to meet the heat, to remove the heat and solution evolved there. This is necessary in order to increase the absorption capacity of the water. Okay, so by seeing the figure only we can just put down the theory. Okay, now because of the high temperature water absorbs less. Because of high temperature the water absorbs less refrigerant, that is ammonia vapor. Therefore the strong solution is thus formed and the absorber is pumped to the generator by liquid pump. The pump increases the pressure of the solution up to the 10 bar. Now the strongest solution of the ammonia in the generator is heated by some external source such as a gas or steam. During the heating process, what happens? The ammonia vapor is driven off the solution at a higher pressure, leaving behind the hot weak ammonia solution in the generator. Therefore, the weak ammonia solution, what happens? The weak ammonia solution flows back to the absorber at low pressure after passing through the pressure reducing valve. The high pressure ammonia vapor from the generator is condensed in the condenser to the high pressure liquid ammonia. This liquid ammonia is passed to the expansion valve through the receiver and then to the evaporator. This completes the simple vapor refrigeration system. Uh, Right? Okay. Now, if you see the in real-time factory areas, so this is a simple vapor absorption machine. See here, you are having a door here, a cabin. You are having a readings where the person is checking all the things in this liquid vapor absorption machine, where you are having a flow chart is shown in this fashion. Okay, so here is a condenser. So here you are having a receiver. Whatever the thing, if you are just keeping in mind by drawing 2 or 3 times, it automatically you can learn the diagram. Next. Now, the next topic is the thermodynamic requirements of refrigerant absorption mixture. So what are the thermodynamic requirements to be required for this ammonia refrigerant for this vapor absorption refrigeration system? We'll see now. So there are two main thermodynamic requirements of the refrigerant absorbent mixture as follows. So there are two main thermodynamic requirements. The first one is solubility requirement. The first one is a solubility requirement. So what is the first one? Solubility requirement. The first thermodynamic property is solubility requirement. The refrigerant should have more than Raoult's law. Refrigerant should have more than Raoult's law solubility in the absorbent, so that the strong solution, highly rich in the refrigerant, is formed in the absorber by the absorption of refrigerant vapor. By the absorption of refrigerant vapor. Second one, boiling points requirement. So here boiling points requirement is there should be a large difference in the normal boiling points. So what is the second point says? The boiling point requirements, there should be a large difference in the normal boiling points of the two substances, at least 200 degrees centigrade, so that the absorbent exerts negligible vapor pressure, so that you can minimize the sun. Okay, so that happens in this boiling points refrigerant, boiling points ref requirement, and there should have a large difference in the normal boilings points of the two substances, at least 200 degrees centigrade, so that the absorbent exerts negligible vapor pressure at the generator temperature. So almost absorbent free refrigerant is boiled off from the generator and the absorbent alone returns to the absorber. Next, in addition, the refrigerant absorption mixture. So in addition, almost absorbent free refrigerant is boiled off from the generator and the absorbent alone returns to the absorber. So the refrigerant absorption mixture should possess the following desirable properties or characteristics. What's the first one? It should have low viscosity to minimize the pump work. So high viscosity indante definitely we are having the some problems, that is pump will not work properly. That's why we should have a low viscosity pressure. Next, it should have low freezing point. So freezing point should be very low. Next, it should have good chemical and thermal stability. Okay, it should have a good chemical and thermal stability. Next, the reversible chemical reactions of all kinds such as decomposition, polymerization, corrosion, etc. can be avoided. So these are the main three physical characteristics where we can give uh, the possible refrigerant properties. One is low viscosity, you have to maintain. Next one, you have to maintain low freezing point. So you have to go for the good chemical and thermal stability. Okay, so like this you are dismissing the quality. But next one is what are the properties should an ideal refrigerant should have in this absorption combination. So the properties of ideal refrigerant for the absorption combination are: first one, the refrigerant should have high affinity for the absorber. So the refrigerant should have a high affinity for the absorber at low temperature and less affinity at high temperature. So what is the first point you have to maintain, you have to keep in consider? The refrigerant, whatever the ammonia or you are using for this vapor absorption, you should have less affinity at high temperature and high affinity at less temperature. Simple. Less affinity, high temperature, high affinity, less temperature. So next second point. The combination should have a high degree of negative deviation from Raoult's law. So what is the second point says? The combination should have a high degree of negative deviation from Raoult's law. Next, third one. The mixture should have low specific heat and low viscosity. So if you have high viscosity, automatically break. So that's why he's having high vis. Next, the mixture, that is a solution, should be non-corrosive in nature. So when this type of things are added to the this refrigerant, automatically the machine will get struck and it won't give the long life process. Okay. Okay. Next, a mixture should have a small heat. So high amount of heat also will be a problem for this refrigeration system. So for this vapor absorption system, we should maintain small amount of heat. Next, the mixture should have low freezing point. So whatever the ammonia mixture you are using or whatever the refrigerant you are using for this uh, type of system, so you have to maintain the low freezing point in order to get the heat in constant level. Okay, next, right? So the next point is characteristics. Okay, so there should be a large difference in normal boiling points of the refrigerator and the absorbent. So these are the 7 points you have to keep in mind whenever you are using the refrigerant, that is ammonia, in this store, right? Okay, next. So we have completed the thermodynamic requirements of refrigerant absorption mixture, the properties of ideal absorption system. Now, the next topic to be discussed is domestic Electrolux. So the name you have heard Electrolux. What's the meaning of where you have heard Electrolux? Electrolux. So the Electrolux or ammonia hydrogen, right? The Electrolux domestic refrigeration system or ammonia hydrogen. Apart from that, you are having uh, steel shell or glass type of metal like this you are having for this system. So now we'll discuss about domestic Electrolux or ammonia hydrogen, right? Okay. Now see the figure, see the description. The domestic absorption type refrigerator was first invented by the two Swedish engineers Carl Munters and Balzer von Platan in 1925 while they were studying for their undergraduate course of Royal Institute of Technology in Stockholm. So in the Stockholm, you are having an engineering college, that is Royal Engineering. Mm, So here, here, if you see the diagram, so in the last slides I have shown the diagram. These are also similar type of diagrams, right? So the domestic absorption type of system were called invented by two, right? See here. So for this place, for that place, it is totally change, right? So the first idea was developed by the Electrolux company of Luton, England. That's why the name has been continued like that. And finally, by Electrolux, they have been just adding, and it has been centered. So here, if we see the first one, where here, so whenever the gas is getting burned, it is passing into the ammonia vapor through the rectifier, and it is passing into the condenser. So if you are kept like that, so what happens here? So it is passing from condenser to the evaporator in the topmost three process. Ultra-absorbing, right? So here you are having the heat exchanger, here you are having a rectifier, here you are having a condenser, here you are having evaporator, and you are having a absorber. So instead of compressor, here you are using the name absorber here there sorry, it may be some sort of examples, but here you are having a generator, rectifier, condenser, evaporator, absorption system, and a heat exchanger. So if you by heart these components, then automatically you can draw this domestic Electrolux system, right? Now, the domestic absorption system was first invented by Swedish engineer Carl Munters and Balmer Plan in 1995 while they were studying for their undergraduate courses at Royal Institute of Technology. So the idea of the first developed by the Electrolux company of Luton, that is by the an example, right? Right. So here, so you're having this type of components in this system. So if you see the original type of system in factories, you can see this is an absorption type of refrigeration system. Absorption type of refrigeration system. So this type of refrigerator is also called as so and okay. Okay. Now see here the actual absorption machine. This type of refrigerator is also known as what? This type of refrigerator is also known as three fluid absorption system. Okay. So the main purpose of this system is to eliminate the pump. Okay. The main system of this three fluid system is to eliminate the pump so that the absence of moving parts, the machine becomes noiseless. The three fluids uses in this system are ammonia, hydrogen, and water. So the three components that are being used for this system is ammonia, hydrogen, and water. The ammonia is used as a refrigerant because it possesses most of the desirable properties. It is toxic, but due to the absence of the moving parts, there is very little chance for the tire, right? So they're having little chances for the leakage, and also the total number of refrigerants uses are small. The hydrogen being the lighter gas is used to increase the rate of evaporation of the liquid ammonia. So as we have discussed earlier that liquid ammonia is a case chloride, right? So the liquid ammonia plays a vital role in this process. This is used in the low pressure side of the system. The water is used as a solvent because it has an ability to absorb ammonia readily. The principle of the operation of a domestic Electrolux type of refrigerator is shown in the figure. Now, the strong ammonia solution for the absorber throughout the heat exchanger heated in the generator by applying the heat from the external source. So, we are showing the external source into the pipe, and so that we can remove the any excess material he is just she's informed. So okay, next, the ammonia vapors in the condenser are condensed by using external cooling source. The liquid refrigerant leaves the condenser flows under the gravity of evaporator where it meets the hydrogen gas. The hydrogen gas which is being fed to the evaporator permits the liquid ammonia to evaporate at the low pressure and temperature according to the Dolman property. Next, what is the time? Okay, now the so here the COP, the mixture of ammonia vapor and hydrogen is passed in the absorber, where ammonia is absorbed by the water, while hydrogen gets separated. Hydrogen rises to the top and flows to the evaporator. Right. So this is about the hydrogen peroxide, also the gas what we are using. Okay, so if you see the coefficient of performance of this refrigerator, COP is equal to heat absorbed in the evaporator, heat absorbed in the evaporator divided by heat supplied in the generator. So the COP of this refrigerator is the heat absorbed in the evaporator, heat received from the generator, right? So based upon this formulas, we have some formulas, right? So we can uh, keep an eye on that 5 papers, right? So the COP is equal to heat absorbed in the evaporator divided by the heat supplied in the evaporate generator. Now based upon this, we'll start a problem so that you can come to know how depth it is. It can start, right? Now I'll read the question. Where is okay? The total pressure maintained in Electrolux refrigerator is 14.17 bar. 14.71 bar. The temperature obtained in the evaporator is -15 degrees centigrade. The quantities of heat supplied in the generator contains all the contains all the dashboards. So contains all the other systems, right? The quantities of heat supplied in the generator is 418.7 kilojoules to disassociate 1 kg of vapor and 1465.4 kg of for increasing the total enthalpy of NH3, right? The enthalpy of NH3 entering the vapors of NH3, right? So here you are showing number of NH3, that is the enthalpy of NH3, environment therapy of NH3. Next, so we're having the other one. So based on that, take the following properties of NH3. So we'll stop the class here. We'll discuss the class in the tomorrow's class. So we are having a problem, and later we switch on to the other type of vapor absorption system. Okay, right.